Universal Time.
I am in radio contact.
Today on the bench, it is the Advanced Computer Controls RC-850 repeater controller. So this is a later model RC-850 because it has the brown case with the orange logo on the front. There are some out there, the older ones have a blue case. This one also has the front panel LED display option. And over here on the right is local speaker volume control, a selector switch for whether you want to hear the transmitter or if the phone patch is in use, and a mic jack, which is either for ICOM or Kenwood mics, depending on how it is wired internally. So we'll take a look and see if there's anything wrong with this. So the back of the unit is where you interface to your repeater. We have RCA connectors for the various audio signals, transmitter output, receiver input, link 1, link 2, I believe that's spare one, so you can have a third link port. Your digital I/O plug here has your push-to-talk and your core signal. I'll have to look at some reference photos of the version 3.8 unit that I have to see if this is right. I think someone might have added these. As I recall, my 3.8 unit has 2 reds and 2 blacks. This doesn't really look right. Over here, we also have a Cinch Jones style power plug that the 2 positives, I believe one was for battery and the other was the power supply, and we have a separate digital ground and an analog ground. The connector here would be for the what was it, the computer control interface option. It looks like our analog connector is missing, and we also have a number of RCA connectors that are spares that the user can put what he or she wants added extra. The phone patch cable would come out this hole, and interestingly it was the normal RJ11 style phone cable that was just like a pigtail hanging out of these if you had the phone patch option. So let's get it open and take a look inside. Okay, so we have the unit open. Give you a quick tour of what I can see. So over here on the right we have the main motherboard. Attached to the main motherboard we have the MX2 memory expansion unit. So it looks like this unit is equipped with version 3.42 of the software, which is the last version you can run without having the computer expansion board, which should sit here, but someone sort of made a weird Mickey Mouse interface and put it in the hole instead. We have the, I believe it's a Redicon retrofit board. So this board is sitting in a socket where the SAD 1024 usually sits, and that's your bucket brigade style analog delay lines. So I guess at some point in time those chips became harder to get, so a replacement was made that stacks up as a daughter board in that socket. Also on the main board, these are the memories. So version 3 I believe, went to the 2 EEPROMs and then the MX2 memory expansion. While I'm also here, this blank portion of the board, that was actually designed for an earlier EEPROM, or I'm sorry, double EEPROM version. It was an early one that needed 21 volts to program. So this was the spot where the 21 volt synthesizer actually went. And that board, let's see, I believe it plugged into this socket and it went, it sat over these memories, but that contained two double EEPROMs that needed the 21 volts to program. So when the 90, what is this? It's a 96, I'm sorry, it's an AMD 9864. When that became available, the MX1 board was no longer needed, just this chip, and you didn't need the 21 volt power supply. Over here to the right, I'm sorry, the left, this is the voice response telemetry board. So this contains the TMS5220C voice synthesizer by Texas Instruments. Not really sure what's going on with this voltage regulator, and it looks like it isn't even connected. Now with the unit turned around, we can see the back side of the LED status display panel. And then these are the audio amplifiers for the speaker and the front panel mic. Someone's also taken the time to label all the potentiometers, so that makes life nice. Okay, I got it wired into the benchtop power supply and the bench test speaker. Let's give it a bell.
RC-850 V3.42.
And came on and it works first time. Alright, I'm holding the unit in reset so we can hear the sign-on message. Also, you'll notice there's a lot of digital noise going on in the audio. That is just the nature of these controllers. They are not very quiet on the audio bus.
RC-850 V3.42.
Advanced computer controls has its origins to about 1980, when a gentleman by the name of Ed Ingber published in 73 magazine a 3-part article titled A Computer-Controlled Talking Repeater, where he describes his repeater controller system as built around the Pragmatic Design's CPU-1A single board microcomputer. Advanced Computer Controls would then go on to create other amateur radio products and repeater controllers, such as the RC-850, which is a scaled down version of the RC-850, and uses less chips as technology became more advanced over the years. So instead of multiple EEPROMs like on the RC-850, this has everything in a single paged EEPROM. They also would create the ITC32, the RC96, the Shackmaster, the Patchmaster, the FM900, which is a remote-based controller that goes on to their repeater controllers, and a few other products. Advanced Computer Controls shut down operations on July 25th of 1995 and sold their intellectual property to Link Communications, now known as Audio Test Solutions, but they were working on a follow-up controller to the RC-850 known as the RC-960. there is speculation that that work in progress became the Link Communications RLC-2. Okay, so to get started on the refurbishment, I think I'm going to remove this regulator because it's not in circuit. So not really sure what that was there for. It is the LM309K. And it looks like the auto patch standoffs are present. So not sure if those came with the case from the factory or if the auto patch board was bought and someone removed it. We also don't have the computer interface board. Maybe in a future episode we'll see about making a recreation of that. And I also want to remove whatever's going on with this interface cable here. Alright, so now we'll go on to remove the motherboard. Someone's put color tape where stuff went, but interestingly it doesn't seem to match the plugs anymore. And we'll start unscrewing the controller. Okay, so now that we have the main CPU board unscrewed, we can take a look at the underside. This connector was going to something on the front panel. We've got some bodge wires. Not really sure if these components were added by the factory or after the fact, so I'll check a schematic on that. And now I'll get my soldering iron fired up so I can get rid of this. Okay, so now we've got the board out of the unit, and I've removed the riser board so we can get a good look. Here's the original 1981 copyright on this board, so I'd guess that whoever laid out the board, I'm not sure if it was Ed or someone else at Advanced Computer Controls, I'd guess they had maybe 1,000 to 2,000 of these made when they laid it out and just kept using the boards over the years. The latest chip I can find on the board is this one with a 1987 date code. Everything else seems to have 1986 on it, so I'd expect this was, the board itself was assembled mid 1987 to late 1987. Also of note, this board has the two chips that make up the DTMF decoder. So it's the, I believe it's the 8860 and the 8865. So one acts as like a pre-filter chip to the other one that actually does like the decoding. Later on, Mitel would go on to create a single chip, the 8870, that combined both these chips into one package. And later products by ACC, they'd have a riser board that had the single 8870, and I've also seen a riser board with the CD22204, I believe the chip is, in place of the DTMF decoder. So I made a mistake earlier. The audio delay line, which usually sits in this spot, is actually the SAD4096, not the SAD1024. The difference would be the length of the delay. And one of the things that we should talk about is how the board generates negative voltage from a single supply. So the audio op amps are supplied with plus and minus voltage, and the minus side is actually derived with an audio amplifier feeding a rectifier and then a capacitor. So there is a chip on the board which divides down the crystal. So we have a 3.58 megahertz crystal that's part of making the DTMF decoder chips work, but there's also a divider after that that gives us a 15 kilohertz signal. So the 15 kilohertz square wave is filtered a little bit and given to an LM386 audio amplifier, which then is half wave rectified to, I believe it's negative 9 volts. See what it says here? It just says V minus, so that could be negative 9 to negative 12, I believe. So while we have the board out, I'm going to take the time and remove all of the electrolytic capacitors off of it, because I recently refurbished one of these where the electrolyte of just about every single capacitor leaked out and did substantial damage to the board. So I'll remove all those, and then I'll get some replacement ceramic capacitors on order. So most of these electrolytics are 10 microfarad, and I believe we've got some 100 microfarad ones, so we'll replace those with a higher quality brand than whatever the factory originally used. Also, I just noticed we have an L7805CV, but this one is so old it is badged SGS. Okay, got all the caps out of the board. I'm going to go through with a cap tester here just to see how bad these guys were getting. Okay, so that one's good. Not too bad on that one. So the consensus is they seem to be reading about 10% low so far, because I've got a mixture of 10s, 1s, there's a 47 in there, there's 10s at 50 volts instead of 35, but yeah, one of these caps started smelling like electrolyte as I was starting to desolder it, so I think we caught it just in time. Alright, we'll eliminate the rat that somebody installed. Not sure what type of repeater they were trying to interface that to. Unless they just came up with their own pinout. But blue and orange here, we're going to, let's see, orange is spare I'm sorry, orange is receive, blue is transmit. And then transmit's also jumpered to another pin for some reason, and the green and the brown pair were our push-to-talk and core lines, it looks like. And we've got one other. For some reason, buffered RX audio was going back into the header. So we're going to make a replacement ribbon cable for our analog connector. The picture I have of the other one that I have is they use a gray connector, so I'm not really sure what brand it is, but I've looked at my supply of IDC connectors, and I think I'm going to go with this amp connector here because it's low profile and it's black, so it'll match the original connector that's on the motherboard. So I looked up this part number and it's by Hiroshi. So I'm not sure if the ribbon connector they used was by the same people or not. But that's what I'm going to go with, and I have a gray 26 pin connector for the other side, so we'll get the ribbon cable made up. So today I'm using this gray 25 conductor ribbon cable. I've sort of approximated how it goes. So I sort of want it to be this length. So I want it to go from this position on the back panel to this IDC connector on the voice response telemetry board. And if I get the phone patch in the future, I want it to go up and over the board. And the other one I have, they route it under the phone patch board, putting all kinds of bends in it, and I don't really like that, so I'm just going to leave enough to go up and over. Okay, we are out of the lab and in the kitchen because I needed more space to make the IDC cables. So this is, what is this? This is the Panapress. So this is the ideal tool for making IDC cables. It comes with changeable dies here. So this is the one that you use for this style connector. I also have for like a couple of dies for the different spacing dip connectors. But of course I do not have the right die for the DB25 and DB9 style connectors. So I think what I'm going to do is just turn one of the other dies upside down so I have a nice flat surface for when I go to do this. And hopefully we can get away with that. Okay, so we're going to take a little bit of time to talk about leaking electrolyte out of the electrolytic capacitors. So when I was desoldering C22 here, I noticed a little bit of a metallic smell. So whenever you desolder a capacitor and it doesn't smell quite right, that's usually a good sign that the electrolyte has started to leak out. So we can see on the positive pad of C22 that there's a little bit of corrosion going on, but we should. It looks like we caught it just in time before it did any major damage to the board. But yeah, that's why I'm removing the electrolytics and replacing them. Okay, with new capacitors on the voice response telemetry board, we can get it mounted again. It's a good idea to when you're mounting a board, don't tighten all the screws all the way until you have the majority of them in, just so you can get everything aligned, and then go back and tighten them down once you got the alignment right. Alright. So here's our new cable that we made. As it turns out, on the 26-pin IDC connector, pin 1 isn't in use. So pin 2 is actually where pin 1 should be. So it's 2 through 26 instead of 1 through 25 for some reason. And also this connector, the pin 1 indicator is in the wrong position, so there's a little dot on the underside of the board to follow. But that plugs in there like so. Then our DB25 goes into the back panel. I was able to find a hardware mounting kit. This one's by ITT Canon. It'll suit our purposes for today. Okay, so our cable's now installed. We'll do some little bit of cleanup. Alright, so it turns out these don't belong, so I'm going to remove them. They did use banana jacks on the blue case, but not on the brown one. I found an article in ACC Notes where they were talking about excessive 15 kilohertz spurs getting into the transmitter, and that was due to the negative voltage generator filter capacitor aging with time. So they recommended changing the value and putting in a low ESR capacitor. So what I'm using is a Panasonic low ESR 100 microfarad at 25 volt capacitor to go in as the filter. And then I'll also be putting in a 10 microfarad non-polar as the in-series capacitor that feeds the half-wave rectifier. I was researching changing the LM386 to something like an LTC 660, but it turns out that part, the LTC 660 is only good for 5 volt in and basically 5 volt out, so since the negative voltage generator needs to be up in the 12 volt range, that wasn't going to work for our application.
RC-850 V3.42.
Well, I can still hear an awful lot of the 15 kilohertz in the audio signal. I think we quieted the data bus down a bit, though. While you weren't looking, I also took the liberty of changing the 1N914 diodes that were in the half-wave rectifier section of the negative voltage generator. And I put in 1N5818. So this is the negative voltage rail here. So I can hear the 15 kilohertz whine come up in the audio output. Something's pulsing on and off. So I'm assuming that is the controller. It's probably over here on the voice response telemetry board. Turning on, there is a digital to analog converter, a 12-bit one, that is used as they use a digital to analog converter and a comparator instead of an analog digital converter. They might not have been available in 1981 when this was designed, but I suspect that what we're seeing on the meter here, the dip is that DAC turning on while it's polling the analog inputs. And we were able to get the courtesy tones running. So unfortunately, that's all the time we have for today's episode, so thank you for watching and try to enjoy yourselves the rest of the day.